The American Space Agency says it's ready to launch its giant new moon rocket next Monday. Yay! So that's going to be exciting, isn't it? They conducted a flight readiness review late on Monday and concluded that all is good to go. And this rocket, known as the Space Launch System, SLS, will send a capsule called Orion on an excursion around the moon. Will this be crewed? Will there be astronauts on board? Well, sadly not. But there will be astronauts on board for subsequent missions, assuming everything goes to plan. So this is going to be exciting. This mission is expected back on Earth for a splashdown in the Pacific Ocean close to San Diego, California on the 10th of October. So we'll all be looking forward to that. Now, last but not the least, news from the University of Glasgow. Future robots could see using new type of electronic skin. Now, this is basically talking about a new form of flexible photodetector which could provide future robots with electronic skin capable of seeing light beyond the range of human vision. So we're going to learn a lot more about that in today's show in our discussion section. But it's really exciting to know that such groundbreaking or cutting-edge research is coming out from the city of Glasgow and the University of Glasgow, to be specific. Fantastic. So let's get on to the next item then. We're going to be getting to know Professor Ravinder Dahiya. Once again, welcome to the show. So we'd like you to tell us a little bit about yourself. We'd like to know a little bit about your background, your early life, where you went to school, where you went to university, and how you came about to be here in Glasgow. So perhaps you could start with your background.
Oh, well, my basic education was from India. I studied up to primary school in a government school, and then went on to a boarding school until 12th, and then did my electronics engineering, also postgraduate from Indian Institute of Technology, Delhi. After that, I moved for PhD to Italy, and that was Italian Institute of Technology where I did my PhD. That's the first time when I learned about robotics and the need for skin in robotics, and that led to also the first let's say beginning about electronic skin was that time. And then I got Marie Curie Fellowship to further advance this research. I spent some time in University of Cambridge. In 2013, I came to University of Glasgow, and rest of the journey you mentioned already about the research articles. It's already reflected in that.
Oh, that's fantastic. That's really nice to know. Yes, indeed. So, it's very interesting. I have a lot of friends and colleagues from India, and I know a lot of great scientists from India. A lot of my textbooks were written by Indians. So what's it like, studying in India when you were growing up? Is it because I've never been to India, sadly. Would you like to tell us one or two things about that?
Oh, well, India is a diverse country. And somehow in the education system, the diversity, inclusion is pretty much embedded right from the beginning. There are so many languages, official languages, so you will find Indians basically multilingual, multicultural, because from north to south you see so many different type of cultures coming together. Almost all religions that you see in the world, they are present there. So in a sense, you get to know through education, your educational life, you get to know so many things that that basically enrich you, and it's a competitive environment when it comes to education itself. As an example, Indian Institute of Technology is getting into them. Success rate is about 1%. So,
Wow.
it's quite competitive. But as you see these days, I hear a lot that India is making lots of progress in various fields. So hopefully there will be more opportunities for people there. Yeah.
Yes, that's fantastic. It's great. So you mentioned robotics as something that seems to be your first entry into this kind of field of research. So do you consider yourself more of a robotics person then, or are you more in the materials end of the spectrum?
Well, I would say the interface of both.
Okay.
Because I use I don't do material engineering as such, but I use lots of materials and use them in the fabrication, to develop the electronic skin, having different type of sensors, different electronics devices, and use them in robotic application as well as in prosthetics. So that way, it's a kind of you could say. Basic research is still in the materials and electronics, but its applied aspect is in robotics.
I see. Wow, that's amazing. So, who would you say inspired you? Was there one person that inspired you, whether known personally or not, in your journey, as it were?
Well, during my master's project, I learned about the amputations and generally number of people amputees kind of. Not just because of accidents, but also many people are by birth, they have to face amputations, and it was a kind of curiosity which led me to look into the sense of touch, and sense of touch that brought me tactile sensing and then electronic skin. Essentially, what happens? The key question came was, what happens once somebody loses their limbs? How do they feel? Right, and that was kind of also a question started a long time ago. I read this quite nice work by Professor Ramachandran from University of California in San Diego, which talks about phantom limbs.
Yes,
and that's basically tells you that once you lose limb, you still feel that it is there. That's why it's a phantom limb. And then the question is, okay, now people have tried to bring a part of lost functionalities by putting cosmetic limbs, but without getting those feelings back, it's kind of hard to gain ownership of these artificial systems.
yes,
And in order to have that ownership means I consider that limb to be part of my actual body. And for that to happen, it must have same weight, it must have same sensory feelings, it must have kind of continue to work for a long time without charging, etc. It must look like my own body parts. So that way, kind of, that was the sort of inspiration where the key question that was coming was, they don't have the touch sensing, and that's an important thing to have if you want to interact with real world objects, if you want to feel them, if you want to, let's say, grasp a beer mug and then want to feel that coldness. Without that coldness, you don't really get a sensation of that you are drinking something good.
Yeah, it's not the same, is it?
It's not the same. It's not the same.
Fantastic. Thanks for sharing that with us. Well, this is the Science Show with Dr. Dada on Jambo Radio Scotland, broadcasting from the city of Glasgow. And we've been having a really interesting discussion with Professor Dahiya from the University of Glasgow about electronic skin and his research in this area. So, Professor, back to you. Just one more question before we get into the discussion section of our show today. So, your field obviously is electronics, the broad research area, isn't it? So, if you could be granted a wish to discover 3 things, what would it be? What would they be?
Well, that's an interesting question, and the answer naturally lies in where I started from. So if I could use my research, let's say, to bestow the low sensory feeling in amputees, that would definitely be a top on the wish list. And to that extent, the rest of the two would basically follow from there, because in order to achieve that, you have to overcome several challenges, and one of them is putting electronics on different type of substrates, making that integration possible. It's challenging because electronics is developed with different materials. Some require low temperature for processing, some require high temperature, and putting them on the same substrate is quite a challenge. So if I could find a solution to that integration of these components on flexible substrates. And then other aspect is again related to manufacturing. If I can manufacture in all these, if I can crack this problem of when, for example, we develop electronics, what happens at the end of life. So we just throw these electronics. We have so many mobile phones, computers, TV, all electronic items at home. We dump them without thinking what sort of damage we are causing to the environment, because this is all full of toxic materials. So in a sense, if we could crack this problem of electronic waste by developing electronics right from the beginning in such a way that after its lifetime is over, even if we put them throw them in the bin and it goes to landfill, it should not cause any environmental damage. Instead, it should degrade into useful byproducts.
Yes.
And those useful byproducts could be, for example, making sort of biofertilizers, etc. So if we could find some way, and that has to start from the beginning itself, where you have to choose selected in a carefully select the materials, and then the low resource, or let's say efficient manufacturing, instead of wasting away a lot of energy, a lot of water, a lot of chemicals in the water bodies. So that way we are also looking into the printed electronics of particularly high mobility materials such as silicon or gallium arsenide, etc. So I think these are three parts. One is the wish list is, in a summary, is what you do at the end,
yes,
which changes life, improves the quality of life of people, and that has implication not just in prosthetics, but the technology, once it is done, it could be also used in wearables and can change the healthcare management, etc. It could be used in many other applications. You mentioned about these fans on wearables, or making there are countries, tropical countries, where people riding on the bikes and putting helmets, and it's also hot, it becomes difficult. So if you can also use some of these technologies to develop, let's say, some sort of small cooling system within the helmet itself, it helps those people in commuting. So what do you do with this technology? How do you do this technology? And basically when you start from here, so that at the end it does not create a lot of problem to the environment. So these are, I would say, sort of three things here.
Yeah, those are big challenges out there. Fantastic. Thank you very much for that. So our discussion then, electronic skin, anyone who would like some electronic skin? When you think about it, when it comes to artificial skin, that's not something we're so unfamiliar with, because if you think about it, things like maybe even tattoos, it's a kind of printing on the skin, isn't it?
Yeah.
And that's what this is kind of all about. But the research,
but that same painting, it is currently it's a from my point of view, it's a passive painting.
Yeah.
It shows you something, you write some character, or you can basically read the character. But if this the same ink that we are using, or same mechanism we are using for tattoo, can also give you health parameters, and if that can be transferred to your mobile phone, that would be kind of a interesting way of looking at electronic skin in healthcare environment.
Indeed.
So the same tattoo becomes a lot more useful than simply reminding if you of some important event or some art.
Yeah, Fantastic. And that brings us to the research focus, which is the news item I mentioned earlier.
Uh-huh.
Future robots could see using new type of electronic skin.
Correct.
Now, this is about, of course, your result, the result from your research group at the University of Glasgow. And in the news release, it says that a team of engineers from the University of Glasgow are behind the breakthrough development, which involves a newly developed method for printing microscale semiconductors made from gallium arsenide onto a flexible plastic surface. Now, the other thing it says in the report is that it's so flexible that you can bend it, hundreds of times, and the device doesn't lose functionality. So it made me think. So, what's the limit to how much you can take? Is it just the hundreds, or is it even more flexible than that?
Well, as far as flexibility is concerned, if you look at, we have tested these devices. Just to give you a perspective, if you look at the needle of syringe, the day-to-day syringe that you will come across in hospitals, you can wrap around that. So that sort of flexibility we are talking here.
Wow.
That's the point. If the curvature is large, of course, that makes it a lot easier. And it's not just flexibility that we test these devices, these prototypes. We also twist them under different bending angles. So that way, because when they become part of wearable system or become part of let's say a robot with curvy surface, these prototypes will experience lots of bending, twisting, different type of mechanical deformations.
Yes.
And that's why we test them for thousands of cycles. And most of publications from my group, you will find that these demos that we develop, we submit, they include them as part of our publications. And many of these results, if anyone is interested, can go to the YouTube channel of my group, which is just if you search Best Group Glasgow, it will show you all those videos where you can see how these devices are being twisted and tested. Yeah.
Fantastic. Thank you very much. So just as a reminder, if you would like to be a part of the discussion, please call, and the number to call is 0743 782 6865. Again, 0743 782 6865. So another question I had about this device that you recently published about is that obviously the device is able to detect light, which is amazing. So actually you can have something on your skin, hypothetically, that can detect light. And it says it can detect from the visible to the infrared.
Ultraviolet to near infrared.
Oh, fantastic. Yes. So even more than that.
Yes, even more than that.
No, that's awesome. So is there any scope for it to become sensitive to the point of maybe single photons? Is that something that is a possibility, or do you see any limitations that would prevent that?
Yeah, in theory, yes. We have not tried that, of course, but in principle, yes. It's kind of it's a detector which it detects the light basically. So it could detect it. We have to, of course, tweak our processes in order to do that, and we need to see under what conditions we are detecting these photons. As an example, if it is detection is at room temperature or is high temperature, because the substrate pretty much plays an important role.
Yes.
So we are using flexible substrates, and these flexible substrates can be any polymer. It could be the same PET as you use in your water bottles, which would melt quite quickly. So it depends under those conditions. But more importantly, when we talk about electronic skin, first thing that comes across in mind is, this is for touch sensing only. But here we are talking about skin that could allow us to see. So when we talk about seeing, we normally relate very quickly to eyes, and we have two eyes, and how is it possible that skin can see? But there are, if you have such a skin all over the body, which means you can see from behind your body and front, so you can see actually things. You can think about a new sort of paradigm where you all around objects you can see, and you construct those images, and possibly use this environment where you have these light sources all around. As an example, in space, if you put such a let's say a cylindrical rod and cover with photodetectors where you have radiation coming from all around, so you could find some applications there. And also, not only this, in this case we are talking about photodetectors, but if it is a quantum dot based LED, one can even see future displays. As an example, currently display that we have on our screen it's a planar. You started with that, the conversation we started, that mobile is planar and the computer screen or TV screen is planar. The reason is that we don't really have those devices at this point which can make it roll like a carpet.
Yes.
That like carpet, you can roll your TV and put in a cupboard.
Yeah.
So we don't have that, and possibly that the kind of direction one could have. We don't have it because most of the, you have seen morph concept 2008. Nokia came with that morph concept, that mobile phone can become your wristband or something like that. And then Samsung came in 2013 with that, the curvy TV.
Yes.
And now we see more from Samsung with these mobile phone which can flex and fold, etc. But you see that fold is just at one point. There are still rigid parts. You cannot roll it. You can fold it. You cannot roll it.
You can't twist.
Yes, you cannot do that.
Yeah.
And there may be application, not maybe, there are applications where you would like to have that sort of twisting. As an example, if you want to wrap a minimal invasive or surgical tool with a kind of electronics, you may have to twist it also.
Yeah.
So in those applications, one can see a sort of display which we don't have today, and that display can give you a lot more information than we have today. We have bendy TV, we don't have flexible TV.
Yeah.
Bendy TV means you bend it once, that's all.
Yeah.
You cannot flex it, or
doing that.
you cannot you cannot crush it like paper or aluminum foil. You cannot do that.
Yeah.
So that sort of thing will happen. Photodetector, quantum LED, and inorganic quantum LED, particularly LED means light emitting diode. Particularly I'm referring here is because the current standard is organic LED. And that's why the large TV screen you see, they have organic LED. You can print them on large area, but that also required encapsulation layer. So if you do not encapsulate, organic LED has very short lifetime, because the performance in the sense that the type of light it emits, that sort of performance degrades very quickly, in couple of months. So who would let's say buy a TV if it doesn't? In 2 months if you don't see that. So for that to extend the lifetime, you encapsulate it, but that encapsulation problem comes that you cannot flex it anymore. It has to be stationary. So it would be good that quantum LED kind of concept that would allow that sort of flexibility, and it's likely to open new let's say avenues in the displays also.
Yes, indeed. The other detail that I picked up on was the fact that your research group recently also developed electronic skin capable of feeling pain.
Yeah.
So what's that about?
Well, pain is an important part of the skin that we, for example, you touch a object, a hot object, let's say a red hot rod, and that leads to thermal pain. Likewise, if somebody, somebody kind of hits you, let's say with a hammer, that's an impact, the pressure related pain. So pain has different dimensions. Problem with pain when we try to develop some solution is that there is no measurable quantity. You don't say like temperature that it's 100 degree or 50 degree.
There's no unit.
There is no unit for pain.
That would be interesting. Imagine if there was a unit. What would it be?
Well, you could say that, maybe in future there will be a unit for pain as well. When before Kelvin, there was no temperature unit. They were not talking about degree Celsius. We were just, those qualitative terms we were using.
But pain is subjective, though, isn't it?
It is. I mean, it could vary from, it could vary, the level of pain could vary from person to person. But coming back to electronic skin, what we did in that case is we have developed skin that has printed transistors. And these printed transistors, they are able to learn with time. So which means if you tap the skin, at the same level of impact on the skin, if you see, then after some time that skin is able to learn that this is a friendly touch, or it's a painful touch. So based on that, it allows robot to react. So that is what we did here. The key points in that case is it's a synaptic, we call it synaptic transistor, because it works like synaptic junctions in human skin, and it is developed by printing, which is a resource efficient process. And then we use that skin to show how robot could learn with time when somebody presses it hard, or an impact, it's kind of an impactful touch. Then robot will react in a quick manner. Reflexes would be higher. And we not only we also developed a thermal pain related work, where we have printed vanadium pentoxide base. It's a vanadium pentoxide is a material whose resistance would change with, or conductance would change with temperature. So we use that and develop this the thermal pain as well.
I see.
Yes. So it's very fast. We tested the skin for cold conditions as well as hot. Normally, when you talk about thermal, people say, okay, room temperature and above. But on very few occasions, you talk about, taking temperature to 0 degree or below 0 degree. So we tested that skin also under those conditions. So when a robot is holding, let's say, ice block. So ice block, you can hold it for some time, let's say a minute or so. After that, it will, because of numbness, you start to see the pain. That's a different sort of pain, and there will be action. Likewise, if a robot is holding hot rod, the action will be very quick. So we tested under these conditions. Yeah.
I see. That's fantastic. Yeah. There's a lot of philosophical aspects to the study of pain as well, isn't there?
Study of pain led to, earlier this year, it was the Nobel Prize that was related to study of pain only.
Yeah. And interesting. Pain.
Yeah.
It would be interesting to know what the unit for pain would be. Anyway, this is the Science Show with Dr. Dada on Jambo Radio, Scotland, broadcasting from the city of Glasgow. Anyway, so let's pick up our discussion with Professor Ravinder Dahiya. So I think one question that's always been on my mind about this field of research is, I can understand the flexibility in terms of being able to bend the devices, right? Bending it, twisting it. But what about stretchability?
Yeah.
So what makes that possible? Because that's a little bit more difficult to get one's head around, isn't it?
Yeah, that's an interesting observation. And stretchability is an important part of skin. You can see with aging, the skin, you can see that stretchability would very much become visible. Also look at elbow, etc. Skin, when you can see that skin in those parts, body parts, it's stretchable. When it comes to making skin, the electronic skin, it's stretchable. So we have different approaches. Some are focused on the materials, some are focused on engineering. As an example, an engineering approach would be to have sort of meander shaped or serpentine shaped the wiring.
Okay, so when you stretch it, it kind of has room.
Correct, it has room that gives that extra sort of stretchability can be obtained. Some materials are themselves stretchable up to a certain degree. They continue to work, and you can use that as well. There are other engineering examples. If you see old days in a telephone, they used to have that coil shaped, and you can stretch it, and you can still have continuity in terms of the signal continuity.
Yes.
So these are depending on application. One can adopt such strategies. Yes.
That's interesting. Thanks for clarifying that. And what about the cost? It sounds like something that maybe would be expensive maybe our listeners would like to know what would that mean in terms of applications, devices.
Well, if you look at the conventional silicon-based technology, it's expensive. But the cost comes down when you look at such things are manufactured in bulk. As an example, one transistor 50 years ago, it used to be about $400. But now, in $1, you can have so many thousands of transistors.
Wow. Yeah.
Right. So it's kind of because we are manufacturing en masse, so that brings the cost down. But I also referred to earlier about printed electronics, which is kind of a alternative route to reduce the cost and make it cost effective, because in case of printed electronics, you are using as much material as needed. So it's a resource efficient. So if whereas in case of conventional micro nanofabrication, it's a subtractive process, which means you are reducing a material and you are wasting away a lot of things.
Indeed.
So that also adds to the cost. So in a sense, manufacturing at scale and printed electronics as a route to manufacture, you can bring the cost quite significantly. It can be down to kind of a normal tattoo that you have. So that way you can have more functionality with the same price.
Fantastic. And just thinking about that for a moment, if we try to go full sci-fi mode here, okay, what would the future be like? What could the future be like? So do you see maybe in future people having, circuits on their skin that maybe emits light, maybe arts,
well, that's very much possible. If tattoo, we see already people enjoying tattoos, so having those temporary sort of, electronic skin instead of a permanent tattoo which cannot change. If you can program it and you can change, can make a different tattoo display all the, every day. It makes a lot of sense. I mean, such a thing, not just to our body, but also in the home environment. Instead of having, discrete, at some bulbs at few points and tubes, you may want to have entire wall, and you just can change the program light. It and change the color every day. So depending on the mood. And it could also reflect in many ways. It could be connected to behavior of a person. And sometimes, the surroundings, they change your behavior.
Indeed.
It could be also used in that sense, but you have to think about large area.
Yes.
And of course, which you already asked, the cost, manufacturing cost, also need to be considered for that to happen.
Yes, indeed. And the other thing that sort of gets my attention is some of these devices. Some of them have been said to be powered by sweat.
Yeah.
And some powered by light from the sun, and maybe even body temperature. Could you make a comment or two about that? Is that something viable?
Well, viability, yes, and it has been demonstrated. That's why I say yes. It has not been demonstrated at a scale. That's a next research question. Any electronic or sensor that device that we have will require some energy source to operate. So in that sense, electronic skin with distributed energy is pretty much needed. And if you can power it from the skin, we have this concept called biofuel cells. So that concept could be used because skin has, these salts, sodium, potassium, etc., sodium chloride, etc. And we have also reported in past a energy storage device, which uses sweat as an electrolyte. So basically, electrolyte is the medium through which you exchange of charges. This takes place, and you are able to store charge in some kind of a battery. Supercapacitor is not a battery; it's a kind of scientific term.
Yes.
is different, but what it does what a battery does.
Yeah, exactly.
So it stores the charge. And likewise, you can have generators. So there are nano generators based on body temperature also. Some devices we have been, students in the school where we read about Peltier effect, when you have two, material with dissimilar junctions. If you put them at different temperature, that temperature itself leads to change in the generation of voltage.
Potential difference.
Yes, potential difference. So potential difference is what you can then use to power your sensors.
Devices.
So if one such material is in the contact of body and one is ambient, so you are already having a temperature gradient which can be used. So that's we call as thermoelectric effect, the thermoelectric nanogenerators. And solar cells, you mentioned about light. So solar cells are very much known to generate energy when light falls on solar cell. That could also be used as part of electronic skin. In fact, we reported a couple of years ago the world's first energy generating skin. Wow. And that was based on solar cells. So essentially solar cells were integrated on flexible substrates, and when light falls on them, they generate energy. But when you are blocking, when you touch a solar cell, in that area you're not generating energy because you're blocked light. So that way you are able to detect the contact as well as simultaneously generate energy.
Yeah. Oh, that's fantastic. Thank you very much. Honestly, we could talk about this all day, couldn't we? There's so much to talk about. A lot of research has been done, and it's really, really impressive stuff. Really nice to have you with us here today. So perhaps we have time for one or two science jokes. Do you have a science joke that you have as your favorite, or that that you could share with us?
Well, I'm not that sort of person.
No problem. I have a few. Perhaps I could share one or two. So this one says, who do you call when you need to determine the value of a resistor in a circuit? Sherlock Holmes. I'm glad you laughed because you got it. And there's another one. The red wire said to the black wire, "Why are you so sad?" Mm-hmm. Can you guess what the black wire said? He said, "Well, I've been grounded."
Yeah, well, that's a good one. Yes.
Yeah, okay, there's no time to explain the meaning. So if you didn't get it, well, you can forget about it. Fantastic. You're listening to The Science Show with Dr. Dada on Jambo Radio Scotland, broadcasting from the city of Glasgow. And next on today's show, we'll be concluding with something a little bit creative, something that will help us keep some of the things we learned today firm in our minds. So we're going to be vibing to a beat. We're going to try to rap to a short beat, and hopefully that will be something that helps keep the point in mind. So DJ, let's have the beat. Thank you. Okay, so basically I've written down a few lines, okay?
Go ahead, please, yes.
So vibe with me. Hey. So let's go. This is truly incredible. When your laptop is flexible, bend the phone, unbelievable. It is also repeatable. More flexibility, with high sensitivity, enhanced capability, machine tactility, electronic anatomy, mimicking biology, for healthcare technologies, unknown possibilities. This is truly incredible. When your laptop is flexible, bend the phone, unbelievable. It is stretchable, and so on. Well, that's all that time will allow us to do today on The Science Show with Dr. Dada on Jambo Radio Scotland, broadcasting from the city of Glasgow. And that brings us to the end of today's show. Remember, if you'd like to keep your eye on the advances and developments in science and technology and its impact on everyday life, just tune in to this show. This is the place to be. If you have any questions, feel free to email us at info@jamboradio.co.uk. And once again, we'd like to thank you for listening to this week's edition of the show. Thank you very much, Professor, for being with us today. And until next week, I say stay curious.